Okay. Oh, we're in the back. Okay, thank you all for coming today to Marcel's thesis defense. I'm so excited and thankful. It's a good thing. I mean, so here's the way it works. Marcel is going to be giving a 45 minutes about seminar, and then his committee will hide in a room next door and will confabulate with him, and then he'll come back to his family alive, hopefully. So that's the format. And so I have a few notes to about Marcel, but I want to say that it's been really a pleasure to work with him. He's a very smart, very funny, very talented guy, and we had a lot of fun out at sea and beyond. So it was really a pleasure to have him with me, and I'm looking forward to seeing him, going wherever he's going. Yeah, we'll see that. But I'm very thankful for that. I'm very honest about it. Not making this up. And so Marcel earned his bachelor degree in the Earth and Planetary Science Institution at UC Santa Cruz in 2014. Then he was a staff geologist at Cotton Shires and Associates between 2016 and 2018. And he started at Moss Landing right before the pandemic. Yeah. So he's a pandemic boy. Was that? A long time ago. Well, I mean, it depends who you talk to. For me, it was yesterday. For you, maybe. And so he received 2 scholarships, the Robert Wiggle Scholarship of Coastal Studies in 2019, the Coast Graduate Student Research Award in 2019, and actually he just finished working on another Coast Award that was given to us for the El Nino season, so he actually went out to sea. So there's actually more mapping that he's done beyond the thesis. So he was on 9 cruises with the NOAA Ocean Exploration and Oceanos Explorer between 2019 and 2024, and has been part-time research assistant at Integral Consulting between 2018 and 2024, and now is working in the NOAA Office of Coastal Service on running bathymetric maps for the use of national bathymetric source. And he's actually working with and for Mia Pavlovich, who's another graduate here in Tom's lab. So, our Moss Landing family is everywhere, and we're very proud of that. I was about to say something else, and I forgot. Will come back to me. Okay, but please join me in complimenting Marcel on this cost-effective multi-beam system yields high temporal and spatial resolution bathymetric maps of the northern Monterey Canyon head. Thank you, Marcel.
All right, thanks, Ivana, for the intro, and thanks everyone for being here today, and as well as those people watching online. And many of you are vital to the success of this project, so I'm glad that you can make it. And without any further ado, I'd like to present my long-awaited master's thesis for Moss Landing Marine Labs entitled "The Cost-Effective Multibeam System Yields High Temporal and Spatial Resolution Bathymetric Maps of the Monterey Canyon Head." And I'm just going to dive right into the 3 main things I wanted to accomplish with this project. And number 1 is to assemble this cost-effective mapping system for these high-frequency and high-resolution surveys of shallow, complex bathymetry. And I just put this image here in the background to show what this type of system really looks like. So you just have a surface vessel that's mapping the seafloor's topography, essentially, with this acoustic signal. And then number 2 is to test the precision of this new system to ensure that reliable repeat surveys could be obtained. And number 3 was to investigate the geomorphic changes that were occurring in the Monterey Canyon region during those preliminary surveys. So the 3 main factors that motivated this study is that right when I joined this lab in about 2018, the seafloor mapping lab at CSUMB had effectively just shut down. So that meant there's no more academic seafloor mapping capabilities in the Monterey Bay area. And we wanted to get that program going again because of number 2, which is that we have these fascinating seafloor features right in our backyard, such as the Monterey Canyon, which plays this vital role in the local environment. So it's a habitat for marine species. It's a big sink for the sedimentary cycle. So you have both the Santa Cruz littoral cell and the South Monterey Bay littoral cell funneling into the canyon head there. And then it also affects these physical oceanography processes such as wave refraction and internal waves. And finally, number 3 is just that the timing was good for this type of project. So multi-beam system costs have been dropping over the last 20 or so years and becoming more user-friendly. So I also had this interest in instrumentation and fieldwork, and it was just a good way to combine all those factors into a research project. And here I just wanted to show a couple more images of the canyon head. So this region is my main study site here. And it's kind of like the gateway to the rest of the canyon because it's the part that's interacting with this dynamic coastal environment. And as a result, a lot of interesting geomorphology is happening here. So it consists of these 4 tributaries that I named 1N, 2N, and then 1S and 2S in the south here. And 2S kind of splits up into these 2 sub-tributaries, 2SA and 2SB. And all of these tributaries are at about a 6-degree grade and reach within about 100 meters of the shoreline there, so really close to shore. And there's also several anthropogenic features within the canyon head. So you have the North Jetty, the Moss Landing Power Plant thermal outfall. That's these 2 chimneys there on that ridge. And then we have our Moss Landing Marine Lab seawater intakes here on the southern ridge, as well as this Kaiser seawater intake pipe. That's this really linear and well-defined feature here on this southern ridge. And all of that is seriously right in our backyard. So we're here at Moss Landing, and the canyon head, and then just down the road we have marine operations, which is where we keep our vessels, and that's just a short trip away from the canyon head. So not surprisingly, being such a striking and impactful local feature, a lot of research has been done on the Monterey Canyon over the last 20 or so years. And I'll just go over some of the most relevant to this project, and especially the ones that inspired me to put this system together. So first up, Charlie Paul and colleagues out of Mbari did these studies in 2002 and 2005, which established that the canyon is in fact active and that sand transport from the coast to the deep sea is occurring through the Monterey Canyon head. So that already gives us this idea that the canyon is a feature that has an impact on our local environment and should be studied further. And then around that same time, Doug Smith and colleagues out of CSUMB published these, or did these bathymetric surveys that were about 3 to 6 months apart between 2002 and 2005. And they saw these preliminary estimates of erosion and deposition happening in the canyon head. So that's this 1.4 million meters cubed of erosion and 350,000 meters cubed of deposition. So pretty significant volumes there. And those surveys also showed that the canyon head is quite active with these common oscillations of 10 to 15 meters occurring at the canyon rim, which is suggesting that frequent episodes of sediment buildup and erosion are happening there. But they also acknowledged that the sediment deposition and erosion cycles might be occurring much more frequently than that 3 to 6 month survey interval at which they were mapping. And then finally, and most recently, Lewis Bailey and colleagues in 2021 published this study about turbidity currents and the triggers. So basically that's this sediment gravity flow that's sort of like an underwater avalanche. And these are the main mechanisms by which sediment is transported from the upper canyon down to the lower canyon, after which it's essentially lost forever from the system. So they're pretty important, but it's still unclear how and where they actually initiate. So Bailey speculated that this rapid or sustained buildup of sediment along the canyon rim is actually more important to triggering these flows than any high energy event, such as a big swell or an earthquake or a flood. However, that study was based on this data where they monitored these turbidity flow events in the deeper axial channel region and away from the canyon head. So there's no actual bathymetric maps obtained of that upper canyon region or of the canyon rim to ground truth what's really happening there. And that really kind of motivated me to put this system together that captures high frequency and high resolution surveys. So yeah, all of that is to say that previous studies have given us this great foundation of canyon head processes as well as the geomorphology and laid out the groundwork for the mechanisms responsible for sediment transport. But there's still a lot unknown about how frequently and where exactly that deposition and erosion is happening. And in order to really ground truth that, you need these high frequency and high resolution surveys to see what's happening at the source. Okay, so now I'm going to get a little bit into the weeds here and dive into this first study objective, which is assembling the mapping system. And first, I'll just go over the different components that are needed for this kind of system, and then I'll specifically go over what I chose for our system. And then I'll also go over a surveying strategy that I developed for this area. Okay, so the first thing you need for this kind of system is a multibeam sonar, or also called the multibeam echo sounder, or MBES for short. And that actually collects the depth measurements. So that consists of this transmit array, which sends out an acoustic signal down to the seafloor that's really narrow along track and wide across track. And then it also has this receiver array, which will listen to the returns of that signal. So then the time between that transmit pulse and the receive pulse will give you the distance down to the seafloor. And through various signal processing techniques, multiple discrete soundings can be achieved across that survey swath. So where this transmit signal intersects the receive signal, you get a depth measurement. And that's why it's called a multibeam, because you're getting these multiple depth measurements across the swath. And then the other thing you need for your system is a positioning unit. So that's needed to orient your measurements horizontally and vertically in space. And that's typically achieved through a GNSS receiver, global navigation satellite system. And that's usually mounted on the vessel, and it's receiving its position information from satellites out in orbit. And then to get these very accurate positioning solutions, you need to correct that GPS signal or GNSS signal with a base station that's nearby and has a fixed and known position. So the vessel is not only moving horizontally and vertically in space, but also moving in every single other direction on the surface of the water. So it's rolling, it's pitching, the heading is changing, and all of that will impact where the transmit signal is sent out. So imagine here the line being the transmit signal, it's going to go straight down, but in this case it's going to go in a much different direction. So in order to account for that, you need an inertial measurement unit, which essentially just measures gravitational forces to establish that correct orientation of the sonar when the pulse is transmitted and received. And then finally, since the acoustic signal is traveling through these variable density layers in the water column, the true position of that signal will change based on how it refracted through all those different layers. So here you have a signal that isn't affected by density layers that would land somewhere over here. And then because of all these refractions that are happening, your true signal is actually over here. So in order to account for that, you need these final two instruments, which is a sound velocity profiler that's ray tracing the signal through that water column, as well as a sound speed probe that's used for measurements of sound speed at the surface here by the sonar for beam forming. Okay, so now onto the actual instruments that I used for my system, and just a special shout out to one of my friends, colleagues, and mentors, Jason Meyer, who really helped me wrap my head around the technical aspects of these instruments and when I was building the system. So for our sonar, which again is how we collect our depth measurements, we have this Kongsberg N3 sonar, and that has a 500 kilohertz frequency, which is giving us this really narrow wavelength and really high resolution. But that signal is going to attenuate quite fast through the water column, so you're getting these kind of shallow ranges between 0.2 to 75 meters. And that's really good for the canyon head because the canyon head doesn't really extend beyond that. And then you're also having this 120 degree swath width with 256 beams. So basically you're getting 256 measurements of the depth across that survey swath. And then it also has a 40 hertz update rate. So you're able to send out a signal down to the seafloor about 40 times a second. So again, it's good for these shallow water systems because the signal's traveling so fast up and down from the seafloor that you're gonna get a good density along the track of your vessel. And then for our positioning system, I chose the SB2 nav site, which consists of a Trimble GNSS receiver and then 2 antennas for accurate heading orientations. And then we use Inertia post-processing software as well as Core Station P210, which is that nearby base station for our PPK corrections, and that results in these horizontal and vertical accuracies of less than a centimeter. And then for the motion system, I have an SPG Equinox inertial measurement unit, and that's seen here. And that integrates into our positioning sensor. And besides roll, pitch, and heading, that also gives us this SBET files, which is a smooth best estimate of trajectory. And the way it does that is it fuses that motion data with the position data together. And then for the sound velocity instruments, we have a AML Micro X sound speed probe. Again, that's measuring the beam forming at the sonar head. And then we were using a YSI XO1 for depth, temperature, and salinity measurements to derive these sound velocity profiles, and we were using this kind of horrendous equation to get that. But yeah, you can see that temperature and salinity have a lot of effect on the sound velocity. So then all those instruments are mounted on this bracket, and you have the GPS antennas up top, our IMU sonar and sound velocity probe down below. And this bracket's made of this 80-20 extruded aluminum, so it's really sturdy, but also lightweight and portable, as well as adjustable. And that was fabricated in-house by Chris Machado, who is now retired. But yeah, this bracket's going to last the project for a year, so thanks, Chris, for doing such a great job on that again. And then obviously, as you can see, all of that is mounted to this survey vessel, which is a 16-foot Boston whaler named Blue, and that's operated out of marine operations. And thanks to JD and staff there for keeping that vessel ready to go at all times and keeping an eye on us while we're out in the field. And then so after acquiring and assembling all those instruments, it was finally time to test it out in the field. And this is my survey area, so it's just outside of the Moss Landing Harbor. And these shallow water environments are notoriously difficult to survey, and this area is no exception. So you have fresh water mixing with salt water that's affecting your sound velocity profiles. You have this really steep shelf coming out from the canyon, and that results in this heavy and unexpected shore break. You have vessel traffic coming in and out of the harbor. You have marine animals, kelp. You have fishing gear everywhere. There's navigational hazards like the remnants of the old Moss Landing Pier, as well as these shallowly submerged rocks off in the North Jetty that people call the dragon's teeth, I think I've heard. And so part of configuring the system was just how to survey this area safely and effectively. So I came up with these 3 different survey designs for testing that system. And the first is just this canyon head overview. So that consisted of these north to south lines and then east to west lines along the tributary. And then that was just to get a general sense of the extent of the canyon head at that time. And it hadn't been surveyed in a while, so we just wanted to see where all the canyon rim regions are, and then also identify various features that we could use for our tests. And then it also consists of these 6 sound velocity profiles. So that was to get a good representation of the water column there and how it's changing spatially and temporally. And then the second design was just this patch test survey, which is necessary to account for any slight misalignments in the mounting of your instruments relative to each other. And that consisted of these 4 lines that were surveyed at different orientations and different speeds and over different features, just as was necessary to complete those calibrations. And then finally, we have the patch test and canyon head surveys, and those were conducted. There was 4 of those, and basically that's the combination of getting good patch test data and also getting a snapshots of the canyon head's geomorphology at that time. So in total, I had these 5 patch test surveys, 4 here and 1 here, and then basically 5 snapshots of the canyon head. So 2 snapshots here, and basically 3 snapshots here because these January 19th and 20th surveys were back to back. So after putting the system together and then figuring out a survey strategy and finally getting everything to work, which took an extremely long time and a lot of troubleshooting, I could finally turn to determining how well the system actually works. So testing the precision, which was important since we wanted to conduct these repeat surveys to measure changes that were happening in the canyon head. And then specifically, I tested 2 things. Number 1 was to what effect these post-processing strategies have on the precision of our system. And number 2 was to test what the effect of slope and depth had on our precision. And before I dive into those tests specifically, I just wanted to give an overview of accuracy and precision because they do differ a little bit, and I'll be using both terms. So accuracy is how well your data represents the real world, and that essentially measures correctness. So here you see all the points that are kind of far apart, but near the actual target, so that's accurate but not precise. And then precision is how well your data measures previous data, so that measures repeatability. And here you see that all the points are close together, but not near the actual target, so that's precise but not accurate. And the go-to way for these accuracy calculations for multibeam systems is typically through what's known as the total propagated uncertainty model. And that basically combines all your manufacturer-specified accuracy thresholds for all your instruments, so like your IMU, your sonar, your sound velocity profile instruments, and then also uses your estimated errors from your physical measurements, so like your offsets between all your instruments, and if you're using tides, your height uncertainties. And it combines it all into getting one accuracy per depth value, basically, which sounds really good in theory, but it doesn't account for all of those errors, because some estimating still exists in this model, and also you can have these field factors that degrade the assumed accuracy, so you can have an increased sea state or unexpected changes in the water column or GPS outages, sonar interferences, or just user errors, so applying in the wrong multibeam settings or taking inadequate sound velocity profiles. And then precision, on the other hand, is much easier to determine and essentially just requires mapping the same region repeatedly, assuming that no change is taking place there and comparing how well that data compares to itself. So this way also factors in those environmental variables and user errors and doesn't rely on these assumed accuracies. So since the goal for the system was to detect geomorphic changes that were occurring through these repeat surveys, precision actually works well to quantify how much of that change observed can be attributed to real change versus mapping uncertainty. Okay, so now I'll just go into the methods of how I tested these various post-processing parameters, and specifically those parameters were the positioning method used, the patch test offsets applied, and the sound velocity profile frequency. And I used my back-to-back January 19th and 20th surveys for this. So I extracted both of those surveys for the positioning method as a PPK solution. So again, that's going to represent our ideal case scenario. And then I also exported both of those as an SBAS solution, which is kind of the fallback if we don't have a base station to correct our positioning data with. And then I also extracted both of these surveys with no patch test applied, with average patch test applied, so an average of all the 5 tests I did, and then survey-specific patch test applied, which again is going to represent that ideal case scenario. And then for the sound velocity profile frequency test, I used the November 11th survey with these 6 sound velocity profiles, and I exported a version with no sound velocity profiles applied, so just using the surface sound speed there, and then just using one sound velocity profile, so I chose this deepest one here, and then again our ideal case scenario with all 6 sound velocity profiles applied. And here's the results of all those tests over the entire Canyon head region. So on the x-axis we have all the different tests, so positioning test, patch test, sound velocity profile test, and those are separated down into their individual components. And then on the y-axis we have the standard deviation value, which is going to represent our degree of precision. And as expected, the standard deviation value for the SBAS solution is higher than our PPK solution by about 3 centimeters. So our ideal case here is about 10 centimeters of precision. And then for the patch test, the lowest standard deviation is actually when we have our average patch tests applied. However, all of those tests show pretty low standard deviations, which is kind of surprising because we're actually removing that bracket every time we survey, so you would think that you need to do a patch test every single time, but maybe it's a testament to how well Chris built the bracket, because even when you have 0 offsets applied, it's still giving you a pretty good precision value, and that might be because the instruments are all really squarely aligned to each other on that bracket, and then also when you remove the bracket, you don't actually unmount all the instruments, so the reference frame is always the same when you put it back on. And then that's really a nice result because it kind of suggests that we can use these average offsets for our surveys, and those patch tests take a long time to conduct, so it's good not to have to do them one every single time. And then for our sound velocity profile test, we see that taking no sound velocity profiles results in this much higher standard deviation than even just taking one sound velocity profile, so that kind of suggests that you should at least take one sound velocity profile so your beams are ray traced appropriately. And then I also ran this precision analysis on this seawater intake pipe, and that's because it's this really well-defined feature that's not moving, or we know that it's not moving, and it's also very linear and has these sharp slopes on each side. And so it's just really good for comparing 2 maps together because you can align those. And we got the standard deviation value of about 9 centimeters here, which is kind of similar to that ideal case scenario of 10 centimeters that we got for the entire canyon head. And at a 95% confidence interval, that's between 18 to 20 centimeters of standard deviation precision. And so we see that changes observed over that 20 centimeter range are 95% likely to be real and not just mapping uncertainty. And now I'm going to move into that slope and depth analysis for the precision. And the reason for these tests is because there's a few physical limitations to keep in mind when using a multi-beam sonar. And one of those is the approach angle, especially with regards to slope. So like seen in this image, a signal traveling from up above at an angle will get either scattered or obscured by these steep features. And that's exactly what we see in, this is actually raw data from our multi-beam. So this is over the Moss Landing Power Plant thermal outfall chimney. So you can see that these steep walls don't get very many returns on them. And yeah, and then the other big one is the depth of your survey area. So the further away your signal travels, the more dispersed it'll be. So in a deeper survey area, you'll get this larger beam footprint on the seafloor. So that's going to reduce your density. And then so for this analysis, what I did is I made a difference raster between the January 19th and 20th surveys. So I have my difference values here. I made a slope angle raster of just the January 20th survey, which is just one of those surveys. And then I also made a depth value raster of that January 20th survey. And I extracted every single grid cell from these rasters and got these 245,000 data points. And each of those had an XY position to correlate all those together, and then a depth value, a slope value, and a difference value. And mostly I was just curious to see if an increase in depth and slope had any effect on the difference value observed between those two maps. So on the x-axis we have depth increasing from about 0 to just over 50 meters, and on the y-axis we have slope angle increasing from about 0 to 80 degrees. And the points are all colored by the differences observed. So these darker points are low differences and these lighter points are higher differences. And just looking at this, there's not really a trend discernible here. And I did run a multivariate regression analysis on this and just got a 0.148 R-squared value. So no statistically significant trend there between increase in depth and slope and the differences observed. But I just wanted to dive a little bit deeper into this. So I only filtered out the higher difference values, which I defined as over half a meter. And you kind of start to see a little bit more of a cluster happening in this higher depth, higher slope region, but still not anything too eye-catching. And then I also filtered out the extreme differences, which I defined as over 2 meters. And here you kind of start to see more of what I was expecting with these clusters in these high depth and high slope regions happening. And just looking at it spatially over the canyon head, you can see even more clearly that these higher and extreme difference values are popping up in these high depth areas and especially on the high slopes. And also on our Moss Landing Power Plant thermal outfalls. So kind of as is expected, that lines up with those physical limitations of the sonar. Nevertheless, only about 1.6% of all those soundings are that higher and extreme difference. So overall, it seems like this multibeam is quite good at handling these complex survey regions like the Monterey Canyon Head. And that might be because it's specifically designed to map in these areas, and also that we always survey on the most ideal conditions when we know we can get the best maps possible. And then finally, I'll just go over the last study objective here, which is investigating the geomorphic changes that were occurring in the canyon head throughout my testing of the system. And although this is not the main focus of my thesis, this is kind of the most interesting because it's where you really start to see this system being put to test and seeing what it can do. And I split this up again into 2 sections, a cross-analysis section, and then comparing some of those changes I observed with swell events. And starting out with the cross-section analysis, I just took 5 of my most complete surveys, so every survey besides the patch test survey and the canyon head, or one of the back-to-back surveys where no change was observed. And I plotted these 5 cross-sections across each of those rasters, so 2 in the northern tributaries, 2 in the southernmost tributaries, and 1 all the way across the canyon head from south to north. And here's the results from that cross-section analysis for the northern tributary region. So here we're specifically looking at tributary 1N and 2N, so that's 1N here and 2N here. And on the x-axis we have the distance along that cross-section, and on the y-axis we have the depth. And so in tributary 1N, so this one here, we see that we start out with this baseline elevation, and sorry it's kind of hard to see on this projector, but it's basically this lowest line is our first survey, October 23rd. And then throughout the next few surveys, so November 11th, December 18th, December 5th, December 18th, we see the steady accumulation of sediment happening in this tributary. And then on January 9th, January 20th, we have a big erosion event, so all that sediment erodes out, and we're kind of restored back to this baseline elevation that we started with on October 23rd. And then tributary 2N shows a slightly different story here. So on October 23rd, our first survey, we start out with this upper elevation here. And then November 11th, December 5th, there's not much change happening here. And then sometime between December 5th and December 18th, so a 2-week period, we have this massive erosion event happen. So we lose a ton of sediment, and now we're down in this lower elevation on December 18th and January 20th. And then in the southern tributaries, we see an even different story. So here we're mostly seeing just some slight sediment accumulation happening at the very rim of the canyon. And that's true for both these 2SA and 2SB tributaries, with maybe some slight sediment accumulation happening in 2SA or some bedform migration there. And then here's that across section, so again from south to north, and this is if you were looking into the canyon head from the shore. And these northern tributary regions are again showing a lot of change happening, and these southern tributaries showing not much change at all. And then also tributary 1N is kind of interesting because it shows this most frequency of change. So every survey has a different elevation here. And then tributary 2N just shows the biggest magnitude of change, but not much variability here. And the takeaway here is that those 5 surveys represented the highest frequency of high-resolution maps of the canyon head to date. And the biggest takeaway is that having this high-frequency data set is really the key to understanding what's happening in the canyon head as a whole. So the best example is that northern tributary region, where this is a difference map between the first and last surveys, so 3 months apart, basically showing no change happening in that northern tributary region, whereas in reality we see that there's been a full cycle of sediment accretion and erosion that happened in that tributary. And then it's also interesting to see that tributary 2N, that we see that that's constrained to this 2-week period between December 5th and December 18th. So we know that that flow, that failure didn't happen just like consecutively over that 3-month period. Okay, and lastly, I just want to do a preliminary comparison of the swell events that came through with the changes I observed in the canyon head. So I took every single one of my surveys for this, but I just show the results that are kind of the most interesting and important to that Bailey hypothesis about sediment deposition being more important than any single high energy swell event to trigger these turbidity currents. And so I got my swell data from this seeded buoy 185, which is out in the Monterey Bay during that time. And the plot here is showing swell heights over time. And all my surveys are marked with these red markers here. And then on the left, we have a difference map showing the differences observed between 2 surveys. So these are going to be my October 23rd and October 27th surveys. And the red is showing erosion, and green is showing accretion here. So this is interesting because we have this massive 7-meter swell event that came through. But the changes we observe in the canyon head are really not too drastic. So we just see slight sediment erosion, accretion, and maybe some bedform migration here. And on the x-axis, on the cross-section, we see that on October 23rd, so before that swell event came through, we were at this baseline elevation. So that was before all the sediment had accumulated. And then as we saw that sediment build up through the fall and winter period, we had this time period here between December 18th and January 19th with these several significant swell events, but nothing as big as that first 7-meter swell event. And here we do see this big failure happen in the northern tributary region. And again, we see through this cross section that by then we had all this sediment that had built up. So basically, you had this smaller wave event trigger this big failure. So that kind of backs up Bailey's hypothesis and also makes a lot of sense, because you're not going to have sediment failure if there's nothing there to fail in the first place. And that might mean that that October 23rd survey was basically this baseline elevation, like maybe the bedrock of the canyon there. That's not going to fail. And then tributary 2N shows a slightly different story though. So here we have this really big failure in tributary 2N. And that occurred in this 2-week period between December 5th and December 18th, when we had these pretty significant swell events. But from the cross-section, we see that that sediment had actually been already built up in the canyon head throughout that whole fall and winter period, where we had these massive swell events come through, and several other large swell events that came through. So this may mean that sediment deposition is not actually the only thing affecting those failures or these big swell events, and maybe something else is at play. So maybe there's the swell duration, so this is kind of an extended swell duration here, or even the swell direction, as well as the swell period, which is all going to affect how the swell refracts through the canyon head here. And finally, obviously I'm just speculating here that these swell events even have anything to do with the changes that we observed in the canyon head, but it seems to be backed up at least partially by this relatively long period of really low swell events and not much change happening in the canyon head during that time. And since this was meant just as a proof of concept, I didn't dive too deep into analyzing these swell events, and hopefully this motivates future studies to keep that high frequency and high resolution surveys going and shed some light on what's really happening in the canyon head through that. So in conclusion, the system was obviously assembled, and we achieved these beautiful high-resolution maps of the shallow complex bathymetry. And through the precision testing, we can be 95% confident that the changes observed over 20 centimeters are likely real and not just mapping uncertainty. And then the system also seems to do quite well at mapping on steep features and the depth limits of the sonar as a whole over the canyon head. And then finally, the system can be set up within just a few hours, and it's relatively turnkey. So also our proximity to the canyon head really gives us this perfect opportunity to keep learning about what's happening in this complex region. And like we saw in the geomorphic change section, these high-frequency surveys really are the key to seeing the full picture and ground truthing what's really happening in the canyon head region. And I just really hope that this system will keep being used in the future studies and for learning how these events are happening. Yeah, and then also observing long-term trends, or maybe even seasonal trends, or maybe even seeing what impact the canyon head has on local beaches. So if sediment is eroding and funneling into the canyon head. So overall, I think there's just a lot of potential for future studies using this system. And with that, I just want to say thanks to a few people and organizations without whom this project would not be possible. And mainly, I wanted to say thanks to my committee members, Ivano Yellow, Tom Connolly, and Patty and Pietro, for diving into hydrography with me and just entrusting me to take on this project, as well as some Moss Landing Marine Lab staff members, including John Douglas and Chris Machado and Tara Egging. And also a special thank you to everyone who helped me with the survey. So that's Mia Pavlok McAuliffe, Annie Bodell, Aaron Hisaya Caron, and Emily Montgomery. Yeah, thanks for your time and good tunes and friendship. And then also to my mentors outside of Moss Landing Marine Labs, including Shannon Hoy and Jason Meyer, as well as Craig Jones, for sharing your knowledge and trust in me, and that enabled me to pursue this field. And also I want to acknowledge the Robert L. Weigel Scholarship for Coastal Studies and the Postgraduate Student Research Awards, as well as QPS, AML, and SBG for supporting this project in one form or another. And yeah, without that generosity, these purely academic studies would not be possible. And last but not least, thank you to all my friends and family who have always been there and are here today in person or online or just out in the world somewhere. And yeah, thanks for always being there. Okay, and with that, I'll open up for questions. Hectic, too. Yeah, seriously.
All right. Do we have any questions? is on.
Hey, great talk. So I'm curious, because you have these time points in December and then in January.
Yeah.
You saw the kind of largest difference in mapping between the two December time points. I'm curious, because there was a really large storm after that December time point, but before the January. Did you see effects from that storm? Or was it more the swell that happened before the storm that you saw effects from?
That changes the geomorphology in the canyon head?
Yeah.
So you're talking about like a storm, like a rainstorm?
Well, it was the storm that like had flooding, and it was that really big one, right?
Was that in 2021 or 2022? Sorry, these surveys were all from January 2021 and 2022, but yeah, I think like a big storm will obviously impact the geomorphology that's happening there. I'm not sure exactly if like a rain event would, which is possible, I guess, because you'd have a lot of like water coming out of the Elkhorn Slough. But yeah, I'm not sure, and obviously like I think there's a lot of factors at play too. Like I think swells have something to do with it, but maybe also some outside events. So maybe there was like a little earthquake or something. Who knows?
No, we went out after the storm. The picture you showed at the very end was actually.
Oh,
Yeah.
the huge swell event.
Yeah.
Yeah, we didn't see too much change happen in there, but we also didn't survey the whole canyon head.
Was that?
We also didn't survey the whole canyon head right after that storm, so it's kind of hard to tell if maybe some other areas changed. But
Yeah. The problem is that when there are storms, it's really hard to go out.
Yeah.
Although we did, as you see.
That was super interesting. Thanks, Marcel. Question, though, how soon after a storm event can you typically go out? Like, are the currents too strong for a few days, or the swell too large for a few days, or can you get out pretty quickly after?
yeah, I think it kind of depends. And the ideal conditions that we're looking for is like a high slack tide, so anything over 4 feet. And then swell heights, we usually look for like less than 2 meters, so less than 6 feet about. And then obviously there needs to be no rain because we don't have anything to cover ourselves. And then also no wind, right? So like we don't want to be out there just rocking on the water because the sonar is going to get this bubble sweep happening, and air bubbles covering the sonar are going to affect the signal that's coming out. So I think it's just super variable, and that's just the nature of the field work is like you have to wait for these ideal conditions to line up, especially with the vessel we're using, which is yeah, pretty like nimble.
Small boats. Thanks.
Small boats.
Please.
Good job. You mentioned cost-effective and less expensive than many other multi-beam systems several times. How much?
Oh yeah, good question. So I actually don't know the sonar head.
I was going to speak to that. I wanted to close, but actually,
We can leave
the
it.
opportunity?
Yeah.
So this project, thanks to Marcel, it's actually a lot of people chipped in, like really some of them money. Some of it came from the College of Science. They gave out actually about the sonar head early on, and then I can't even remember how many people just gave a few donations to put this together. And the amazing work that Chris Machado did building the frame. And so this is something only in Moss Landing can happen, really. And I don't know if it could happen now.
Yeah.
Frankly, this is like such a great demonstration how, such a small lab can put together an amazing system. But, in terms of cost, I think it ended up in the end probably $150,000.
Maybe less.
Maybe, well, they had, yeah.
How much was that? Because everything else was like 70K, I think.
Yeah, so the head was about, yeah, so you're right. Maybe the head was like 50,000, so maybe 120,000. And then free software.
Yeah, the big thing is the free software from QPS.
And free labor. I mean, free labor. No, I'm talking about the building.
Yeah, that's.
I mean, if you were to buy, custom made, so, I mean, they brought the boat up here. For a while, the whaler was up here just to make the design. So again, I'm so thankful to, to all the people that collaborated. But
Yeah,
this is like
absolutely.
the spirit of this place, right? So,
Okay, one more, and this one's for Marcel.
Okay, got it.
Many in the deeper parts of the canyon, many of the discoveries Mbari and other folks have made have been opportunistic kind of observations of losing moorings and having them swept down during turbidity currents and things like that. The multi-beam maps that came first kind of gave an idea that things were changing over time, but then these events were actually trackable by the physical movement of known objects. Do you think that that approach might be possible in the shallower parts of the canyon? Some sort of instrumentation to both sense the current changes or the events that happen, but then also to track the movement.
Absolutely, yeah. I think that's a great idea, and also especially since that capturing these surveys every 2 weeks, you see the changes, but you still kind of have to interpret when exactly that happened, because like we said, this is the highest frequency, and it's still every 2 weeks or so, as well as where that sediment ends up. So like sometimes you see a big failure, and then some sediment accumulation, you can kind of guess that that's correlated, where that sediment failed there and ended up here, but having an instrument actually mounted on the seabed there and that moves along would be super helpful to like actually tracking the movement and the exact timing.
yeah, there are also the bad forms, right? I mean, the bad forms are also another indication. I mean, you got really cool data showing how they're accumulating this. Right. So I think Tom,
This one will be quick. I was wondering where your instrument is now, and if there are any plans to use it in the future, since it collects really cool, useful data.
Yeah, good question. Give that one to Mason. No. Yeah, the instruments are all still there, and they're just at marine operations.
we
So
just had the coast rank, so he ran more surveys.
yeah.
And
So
there's a new student that allowed us to take the project.
yeah, so the system is still in use, which is great. I'm really happy about that, and yeah, I think it's such a good opportunity because the system's already built. We have the software available. We have all the hardware ready, and really all it requires is just some like gasoline to go out there and map the canyon. Maybe a few other little things.
And the pilot.
Yeah, but Mason's gonna be taking over the system, so.
And then Tom, and then we take off because he has to go back to class.
So you mentioned you did an analysis on 0 SVP data versus 1 data collection.
Yeah.
And you never mentioned anything if there was a difference between 1 and 6 profiles.
Yeah, so they were comparing like no sound velocity profiles to all sound velocity profiles. So that was more of an accuracy calculation. So we kind of suspected that 6 sound velocity profile is our ideal case scenario. So taking no sound velocity profiles had this much higher level of inaccuracy than just taking 1 when compared to that ideal data set. So yeah, basically taking 1 is like essential to a survey, and if you take no, then you're not doing a very good survey.
But there was no significant difference between 1 and 6.
So the difference between 1 and 6 is that, let me see here. So this is comparing the 1 sound velocity profile to 6 sound velocity profiles. So you have this, what is that? 1 centimeter? Yeah, uncertainty or standard deviation. So if you were to compare 6 to 6, obviously you'd have 0 here. So just 1 compared to 6 is giving you a standard deviation of 1 centimeter. But then not taking any is like 5 times that.
Great presentation, Marcel. Your analysis of the swell events showed some really intriguing patterns, but it's all based on an offshore buoy. So
Yeah.
what ideas do you have for future analysis of waves and how that might affect the sediment and the tributaries?
Yeah, that's a good question. I think, so CDIP actually has these models of nearshore swell. So it kind of takes information, I believe, from all the outside buoys and kind of uses the local bathymetry to derive what kind of effect the swell will have on the near shore. So it's possible to use something like that. And then also recently, I think SCIDA deployed these buoys out at the Pajaro River mouth. So those are all really close to the shore, so that can maybe give you a little better idea. But then obviously the canyon head is this super dynamic environment that refracts swells in all sorts of different directions. So yeah, maybe there's these spotter buoys that are super low cost and you can deploy. I've done some of that for that Integral consulting company, and yeah, maybe something like that just right in the canyon head would be useful to see what's happening there.
Thank you.
A couple more questions, and then we need. Thank you.
Yeah, looking at the graph for the tributary 2N, I saw like the cross section. There was like a bit of a like spike after one of the yeah, that one, the lower one. There's like a little spike after a turbidity event in part of that. And can you explain like what that is?
Yeah, totally. So that cross section is here, and that point correlates to this area here, and I believe that that's some sort of rock feature that's not moving. I don't know how to confirm that. I don't know if there's been like some ROV that's gone down there, but I'm guessing that that point is a rock, so it's an immobile object, and that's why you'd have this sediment flow out, but that thing would remain in place. And yeah, that's a good point.
Nice, thanks.
Great presentation. Thank you very much.
Thanks.
So I'm just curious. The only thing I really know about side scan sonar stuff is that it's like worth a lot of money, and that the big companies doing a lot of the work pay tons of money and build big boats for it.
Yeah.
So,
hear that, Amanda? Pay big money.
is there a lot of like economic value and future interest in small boat mapping in the really shallow coastal areas? Like, how deep can you go with this system?
Yeah, totally. I think the really big one with a lot of money is in shallow water areas is dredging projects. So, so if they want to dredge this harbor mouth here, possibly maybe we could get hired to do surveys and just calculate the volumes of sediment that they're extracting and show them exactly where they need to dredge. So it would save them a lot of money to have these high resolution surveys there, and then also possibly give us a little bit of funding if that was the case. But yeah, good question. I think there's a lot of money in it because it's such a niche thing, and like mapping the underwater topography is not, you can't see what's under there. So yeah, I think people will pay to see what's under there. Yeah, and then as far as research, this system can be used, for these maps, and then also you can derive backscatter data from this type of sonar too, so you can see basically the hardness of the bathymetry. And a lot of biologists will use this for habitat studies to see if there's certain, species that correlate to a certain habitat in the bathymetry.
Cool, thanks.
Yeah.
Okay, Marco, last question.
So my question is kind of the opposite, not going deeper, but going shallower. So what could you take this up into Elkhorn Slough and map, and then how would that be affected by vegetation?
Yeah, good question. And we've actually done that. We've gone up into the Elkhorn Slough and surveyed the whole slough. And yeah, what is it, the pickleweed or something? That's on the bottom is the seagrass. Yeah. That just destroys the signal, so it scatters it all over. But it's actually really easy to tell where there is seagrass because you're just getting this crappy data in those areas. So you can be sure that that's the seagrass area. But yeah, this system can be taken down to about half a meter depth or so, and that mostly depends on the draft of that sonar when it's deployed out off the side of the whaler. But yeah, we've done we've done pretty much the entire Elkhorn Slough, and then also that restoration channel. What's that called? Hester or something? No.
Well, in front of us, the marsh.
Yeah, yeah.
That's the main channel.
Which goes really shallow, but we went on like a really high tide and we're able to survey that.
And we drive around surfers too here in the shallow water. Right?
Yeah.
Yeah. It's kind of,
Yeah, I think there's just a lot of interest in like SAV mapping. So like to be able to look at the bottom topography, but then also get like maps out of it would be beneficial.
Totally. Yeah. Add it to the list.
yeah, that's the plan. That's the plan. Okay. Well, thank you very much. Thank you, Marcel.
All right. Thank you.
Thank you for coming. Very well. So I'm going to pick up the microphone. The committee is meeting. Oh, is there any question from? Sorry.
Daqui uma pra vez.